Hello and welcome back to Dr. Logic awkwardly does logic in her kitchen. The way to learn propositional proofs is to do lots of them and to see lots of them. So in this video, I'm just going to give you two more examples of proofs that involve the derived rules that I've introduced in the last couple of videos, just so that you've got a chance to see the process of proving in action a couple more times before you start trying to do all of this on your own. So whiteboard up, and I think I've discovered the trick to getting things to record right is to make the whiteboard full screen. So hopefully this goes. The first thing that I want to prove is this. We've got the first premise is that S or T implies that S implies not T. Second is if S implies not T, then T implies K. Third premise, either S is true or T is true. And from this, we are going to derive that if S is false, then K is true. So setting this up, we've always got our three initial assumptions, our premises at the very beginning. So just copy them down. S or T implies S implies not T. Assumption one. Assumption two is that if S implies not T, then T implies K. Assumption three, either S or T. And then we want to prove from this, our goal is not S implies K. Now, right away, you can already see that there are some of the derived rules that we could apply before we even look at what our goal is, if you wanted to. So we've got S or T implies S implies not T. S implies not T itself then implies something else. So between lines 1 and 2, we could apply the transitivity rule to get S or T implies K. We could do this. I'm not actually going to do it right now. Similarly, if you look here, you can see that we've got S or, actually, why not? Because here in line 3, we've got the antecedent of the conditional in line 1. So let's actually go ahead and do a bunch of these rules involving just our premises before we even start thinking about our conclusion. So lines 1 and 3, here we've got a conditional. Here we have its antecedent. So conditional elimination allows us to get that S implies not T through lines 1 and 3. This is the antecedent of what we have in line 2. So if S implies not T, which we have on line 4, and S implies not T implies K, again, through conditional elimination, we can get that T implies K. So this is going to be lines 2 and 4. And already things are looking pretty good here. And turns out I didn't actually even need to do the syllogistic rule because since I had the antecedent, I could just do 2 applications of conditional elimination to get to our n. Now I'm going to look at the goal. It's a conditional. How do you prove conditionals? You assume the antecedent and try to derive the consequent. So let's put in a new scope line here, and our antecedent is going to be not S. So, when I first wrote all of these down, I actually had a very different idea about the order I was going to go through this proof, but I think that the way that I'm actually doing it right now is going to be faster. So that's always nice. We are assuming not S, and our goal is to get K. Well, not S, along with the disjunction between S or T, from that we can just conclude T through our derived rule disjunctive syllogism that says, if you have a disjunction and the negation of one of the disjuncts, you can write the other one down. And then line 7 and line 5 together will get us K right away. So this is actually quite a straightforward proof when you've got all the derived rules. So conditional elimination from lines 7 and 5 get us line K. I'm going to scribble out the rest of that scope line because we don't need it anymore. Because here at line 9, we can kind of close that one off, and we've already got that not S implies K. Conditional introduction lines 6 through 8. So this one actually turned out to be quite straightforward and almost not very interesting. Let's see if the next example that I want to give you turns out to be a little bit more fun. Sometimes it's nice to get something that actually involves a little bit of thought. Here, there were just so many rules to apply, and I just started applying rules, and then all of a sudden I was like, I'm basically at my conclusion. Hardly had to use any of the strategy at all. Anyway, our next one is I'm not going to write it across the top like this. I'm just going to start by writing the premises down individually. Hope you don't mind. So this one, the first one says that L implies that if M is false, then N and O are true. So that's our first assumption. Second one is the conjunction of not N and P. And third one, oh, no, it's just the two. So let's erase that. Our goal here is to say that is to get if L, then M and P. So here I am going to start off following our usual strategy that says, look at your goal. What is the main connective of it? What is the rule that you would need to use to apply to get this? So it's a conditional. I'm going to assume the antecedent, and then our new goal is to try to get M and P. Now, P is easy because I can just do conjunction elimination on line 2 and I've already got it. So all I need to be able to do is find a way to get M. Now, L, our assumption here at line 3, happens to be the antecedent of the conditional in line 1. So apply elimination rules whenever you can as a rule of thumb. So that means on line 5, I can get not M implies N and O. So that's conditional elimination, citing lines 1 and 3. I'm going to just bracket that off so it doesn't get confusing. Now we are in a position where we have done a bunch of elimination rules. We've got a bunch of atoms. The atoms aren't really the ones that we want. We would like to get something involving M. The only premise that we have involving M right now is line 5, but it's negated M and it's a conditional and we don't have the antecedent and we don't have the... Anyway, there's a whole bunch of things here where it's not immediately clear what to do. So go back to our kind of interim goal that we wanted to get M and P. We've already got P, so we just need to get M in order to be able to use conjunction introduction. How do you get an atom if there isn't an immediately obvious way of getting it through one of the other rules? Negation elimination or negation introduction. So what we will do at line 6 is we will assume that actually M is false. We want to try to get a contradiction, and now you should be able to see that this will actually happen pretty quickly because not M now allows us to take advantage of line 5. Through conditional elimination, we can get the conjunction of N and O. So conditional elimination, lines 5 and 6. But we've got not N up at line 2, N at line 7. So we just need to do a couple instances of conjunction elimination. So first on line 7 and then on line 2. And there you have it. We've got our contradiction. So we know that M, in fact, has to be true. We've shown that through negation elimination of lines 6 to 9. And now with line 10 and line 4, we can conjoin these together to get our conjunction M and P. So conjunction introduction, lines 4 and 10. And that's the consequence of the conditional we wanted to form. So we can end this scope line and say, well, if L is true, then both M and P also have to be true. So conditional introduction, citing the entire subproof from lines 3 to 11. There's a couple of other ways that I could go about doing this as well. The fact that we know that N is false means that we also know that the conjunction of N and O would have to be false as well. So I could have gotten not N and O and then used modus tollens to get not M and then double negation to get M. So one thing to recognize with these proofs is that there isn't one right way or one smart way or one quick way or one natural way. especially once we have the derived rules, there are so many routes that you can go through that they all end up just being kind of variants of each other. It's like, well, do you do conditional elimination to go from the antecedent to the consequent, or do you use modus tollens to go from the negation of the consequent to the negation of the antecedent? So don't ever, when you're working through these proofs, say you try some of these on your own without, even though I've given you examples here, you might want to just like pause the video before I've written the proof, give it a go yourself. You might come up with a different way than I did. But that's okay, because as I said, even before I sat down to prove these for you, I didn't necessarily know which way I was going to do it, or kind of the thought that I had in my mind is like, oh, I might take this route, ended up not being the route that I was going to prove. When I'm teaching in person, pretty much every time that I put a proof up on the board, I end up proving it differently than I did the time before. So I just want to kind of remind you guys and encourage you guys to be comfortable with all of these different ways. And if you're working with other people and they're coming up with different proofs, this doesn't mean that your proof is wrong. It just means that there's many different ways of proving these things. So there you have it, a couple more examples. Hope they were useful. As you start doing more of these, you will start seeing repeating patterns, repeating proof methods, the way that you kind of put many different things together. And the more you do, the easier they become. Luckily, doing them is fun. So you can enjoy yourself and educate yourself all at the same time. Am I going to talk about what I'm going to say in the next video? No, I'm not, because I haven't quite decided, but I look forward to seeing you then. Cheers.